read that if you like. This should give you some intuition behind the traveling wave problem. Let's conclude by actually solving for this, this traveling wave solution. I'll sort of get you started on the homework problem, 12.5, in the case of a cubic. So for example, traveling wave for the bistable equation with a cubic function, okay? We can go a bit further than the phase plane analysis and actually get a nice formula for f in this case, although it takes some work and you're going to do some of that work on your homework, okay? All right, so here's our cubic. This is f of u, 0, a, 1, u, okay? And so in this case, if we consider u sub t equals uxx plus now this cubic, then assuming u equals v of psi, v prime is equal to w, w prime is equal to minus sw minus v1 minus v minus a, okay? So the trick that we can employ in this case, right, and this is sometimes used in you know, two coupled nonlinear ODE models, is that we can say that dw dv is equal to dw dxi divided by dv dxi, okay? So I can actually write a formula for the different, or I can write an equation, a differential equation for dw dv, okay? So w dv, if I just divide through by w, but then I multiply through by w, I get minus sw minus v1 minus v minus a, okay? And what we can do is show that this has a solution of the form w equals kv1 minus v, okay? So how do we know that? Well, we could use you can use a separation of variables argument to get this, or a change of variables argument. Okay, but let's just show that this works. If I differentiate that solution and I multiply it through by itself, right, I should get k squared v1 minus v1 minus 2v equals now my right-hand side, which is minus sk v1 minus v plus v1 minus v a minus v, okay? So just for reference, right, this solution w v is going to look something like this, right? So it's going to have the shape that we want in this case. So it's going to look like the sort of shooting solution that we were figuring out before, okay? Now you can simplify this equation here, okay? First of all, by dividing by v1 minus v, we get k squared 1 minus 2v is equal to minus sk plus a minus v, okay? So if we now simplify So if we now equate our terms, right? So our if we equate the terms that involve b in this case, we have minus 2k squared is equal to minus 1, or in other words, k is equal to 1 over the square root of 2. This gives us the positive parabola, right? This is the shape that we want up here. If we equate the constant terms, what we get then is that k squared is equal to minus sk plus a. And I know that k squared is equal to 1/2. And so I have minus s over square root of 2 plus a. Remember, this is a given, and this is the thing we're trying to figure out. Okay? And so if I simplify, then I get that the wave speed is equal to the square root of 2 over 2 times 2a minus 1. Okay? And in the homework, you're going to solve for v of psi in your homework problem. Okay? So what does this mean? Well, what it means is that when a is less than 1/2, I'm going to have a negative speed. S is less than 0. When I have a is greater than 1/2, I'm going to have s is greater than 0. And when I have a is exactly equal to 1/2, then I have that s is equal to 0. So I have a standing wave. In each of these cases, okay, not surprisingly, corresponds to a different case of the nonlinearity, the cubic nonlinearity. So let me leave some space so I can highlight that. What you can show is that in this case, the integral from 0 to 1 of f of y dy is less than 0. In this case, you can show that the integral of f is greater than 0. In this case, you can show that the integral of f is equal to 0. Okay? So in general, f of u's integral determines the wave speed, okay? Because it has to do with how much mass of your phase space you have sort of pulling things up to the high fixed point, or how much mass you have in your phase space pulling things down to the low fixed point. So whether you have a receding wave or a wave where the sort of the up state, the active state, is sweeping into the rest of the domain. Okay. And so remember, right, you have two parabolas here, W and V. One of them goes from here to here, and the other goes from here to here. Okay. So that would be, you know, one of these would be the s less than 0 case, and the other would be the s greater than 0 case here, where it's propagating from left to right. Okay, so as I mentioned, you'll have the chance to dissect this approach a little bit more on problem 12.5 on your homework. That concludes our lectures on nonlinear PDE and traveling wave solutions. We'll do a bit more practice on Monday, and then yeah, you'll have a chance to dig into this on your homework if you haven't started already. All right, see you all later. Thanks.